Good morning students. I am Manpreet Kaur and today we will discuss the cases of that is applications of Gauss theorem. Gauss theorem that we have already done. Again I will recall its statement, that is the total electric flux through a closed surface is 1 by epsilon naught, which is the permittivity, right, times the net charge enclosed by the closed surface. One thing that should be very much clear to you is that he is talking about only that charge which is present inside the surface, right? Only inside the surface. Charge enclosed by the closed surface. Closed surface means which has no end. And the mathematical statement is phi, that is flux. Flux is equal to closed surface integral. This is the symbol of closed surface, right? This loop. So ds for area vector. So this is flux is written as closed integral of E dot ds, which is equal to Q by epsilon naught. This is the statement of Gauss theorem. Now let's use this theorem to discuss the case of electric field due to infinitely long straight charged wire. Because this is straight charged wire, that means we are basically in one dimension. So basically we wish to find the electric field due to this charged wire. Basically this is positively charged. We can also take the negatively charged. Just for convenience we are taking the positive, because due to positive charge electric lines of force always come outward, right? So for this, if anywhere, whenever we have to use the Gauss theorem, our first step is to select the Gaussian surface, right? Gaussian surface means that closed surface, right? Suppose this is the observation point where we wish to find the electric field due to this wire. So for that I will consider that Gaussian surface which will enclose this wire, right? So for that because this wire is infinitely long, so I can't consider the whole wire. So I am taking its portion, that is, let it be this one. I am considering the shape of a cylinder. I am just drawing it in dotted lines because this is just imaginary surface. Don't forget it. Gaussian surface is an imaginary surface which is basically drawn to find the electric field due to any case, due to wire or sheet or something else. This is the point of observation and the distance from this wire is, let it be, r. Now we want to find the electric field here and we will use this formula. We know if we have to write the formula of flux, then we write it as E dot ds, right? We will find the flux due to this Gaussian surface. Now we will consider the three faces over there. Three faces. One is the top surface of cylinder, one is the bottom surface of cylinder, and one is the curved surface of cylinder, like this. Okay, this one. This is the curved surface, right? This is the flat surface. So we have two flat surfaces and one is curved surface. So I have to find the flux due to these surfaces. So I will consider these faces S1, S2 and S3, right? Two flat faces and one curved surface. That means the total flux E dot ds is E dot ds1, right, plus E dot ds2 plus E dot ds3, right? This closed surface I have changed it into three parts: E dot ds1, E dot ds2, E dot ds3. ds1 is what? This is the surface S1. Any small element taken over there, that is ds1. Similarly, here you can take a very small surface, that is ds2, and here very small surface, let it be ds3, right? So these three faces are there, and as this is the positive charge, so electric field will always move outward. That means if I consider this surface, then electric field is outward from this wire, and same is in this case, electric field in this direction in every case. Now we'll talk about the area vector. Area vector is always perpendicular to the surface. Area vector is always perpendicular to the surface. So if this is the surface, that means area vector is along this direction. This is ds1 vector, right? So similarly, this is your ds2. The electric field is in this direction, and if we consider only this portion, then the area vector direction, that means perpendicular to the surface, this is will along the same direction, that is ds2. ds2 is along this direction. Then is ds3, again perpendicular to the surface. This is the bottom surface, and perpendicular to that, that means in downward direction, ds3. So three cases are there. In first case, we can say that the angle between this ds1 and this electric field is 90 degree, right? Then the angle between electric field and ds2 is 0 degree, as they are in same direction. Then the angle between electric field and ds3 is again 90 degree. So now we can write E dot ds equal to, here you must note that when we have to split this expression, then in this expression, in its component form, I am not using the closed loop sign because I have opened it, right? On the left side there is the sign of closed loop, but no sign on the right hand side. So E dot ds1, I will write it as E ds1 into cos 90 degree, because the angle between E and ds1 is 90 degree. This is over the surface 1, S1. Then plus this is E, and angle between E and ds2 is 0 degree. So this is E ds2 cos 0 degree, plus then for third, this is E. Angle between E and ds3 is again 90 degree. So this is E ds3 cos 90 degree, right? And cos 90 is 0, cos 0 is 1, right? So I get E dot ds over the whole closed surface, that is Gaussian surface, is this cos 90 becomes 0, plus it becomes E dot ds2 plus 0. That means the surface area of only those part will be considered, that is the curved part, right? So here E we can take common, this is E ds2, because now E and ds2 are in magnitude form and E is constant here, we can take it outside. Here it is only ds2. ds2 is what? ds2 is curved surface area of cylinder that we have considered as Gaussian surface, right? So ds2 is curved surface area of cylinder, which is basically equal to 2 pi r L, right? 2 pi r L, and L is what? It is the side of the cylinder, this one, right? This is your L, 2 pi r L. Then we will use that E dot ds is basically equal to E into 2 pi r L. That is, I have substituted the value of ds2, integral of ds2 as 2 pi r L, right? Then using the relation of Gauss theorem, that is E dot ds over the closed surface is equal to q by epsilon naught. So using these two equations, I get E into 2 pi RL is equal to q by epsilon naught. But now q is not known to us. Why? Because this is an infinite long charged wire. So q is not defined. So we will use the continuous charge distribution concept, according to which charge per unit length is known as lambda, that is linear charge density. Lambda is what? It is linear charge density, right? So q by L is lambda. So I will substitute the value of q in terms of lambda, right? Because this is infinite long charged wire. So I will use linear charge distribution over there. So I get q equal to lambda L. Then substituting the value of q here, I get E 2 pi R L equal to lambda L by epsilon naught. Then I get E equal to lambda by 2 pi epsilon naught R. Or I can say E is inversely proportional to R, because all these things are constant. That means electric field will decrease as we move away from this positively charged wire. This R would increase, that means E would decrease. That means the graph for E and R would be like this. That means if E is increasing, then R is decreasing, right?